Hi again. Did you try this question? Is it easier this time than before? So we would like to compare the chance of high salary uh, between high tuition graduates and non-high tuition graduates. So the condition is tuition level, and we are comparing, of course, high tuition and low tuition. And the main event of interest is salary, high salary. So the answer is B. The answer is B. And put it to put it in the context, the probability S given T is the probability of the chance of making high salary if you paid high tuition, and probability of S given T complement is the probability of making a high salary if you have not paid high tuition. So these are what we would like to compare in this example. And suppose that we have the joint probability distribution table like this, 2 by 2. S stands for salary, T stands for tuition. And now another exercise. Calculate two conditional probabilities and compare. Determine these two conditional probabilities and see how the inequality or equality goes. Pause the video here. It's too short to stop end a video here, so I recommend you to just pause while you do the math and resume when you have done the algebra. So pause now. And I am going to continue to the next page now. So from the joint distribution table, it's easy. We first conditional probability is conditional on T, high tuition. So it uses the first row. Only the first row observations satisfy the condition T. And the second conditional probability is about the second row. Only the second row outcomes satisfy this condition. So the denominators are different. And we are looking for high salary, which is these guys. And in the end, if you do the algebra, you get 25%, in both conditional probabilities. So this means if you have paid high tuition, the chance of a high salary is 25%. Even if you have not paid a high tuition, still the chance of high salary is 25%, which means tuition has nothing to do with high salary. The data is just, the numbers are made up, so I'm not saying it is true. I don't know if this kind of data exists or not. Just an example. But the point here is it's an interesting case where different conditions imply the same probability. So, and additionally, what's interesting here is if you calculate the unconditional probability of high salary, it is still 25%. So probability of high salary regardless of tuition level. So this is the marginal distribution. So probability of this guy itself is 25%, which means no matter how much tuition you paid, the probability of high salary is always 25% in 3 cases, unconditionally, or if you graduate from a high tuition school, or if you have not graduated from a high tuition school. So in any case, the probability of high salary is 25%. This is a very interesting example and interesting case. So we define this relationship as statistical independence. So we say two events A and B are independent, simply independent, or statistically independent if their one probability is not affected by the other event. The probability of one event is not affected by the occurrence of the other event. So exactly, probability of A is not affected by B, or B does not happen, right? Or equivalently, this is exactly equivalent, mathematically equivalent to this. The probability of B also is not affected by A. So they are, the first line and second line are the first equation, second equation are mathematically equivalent equations. So it doesn't matter what you use. And it is an interesting definition. And there are many ways to interpret, many examples, many contexts. You need to check the independence. For example, in our examples, we have interpreted this way. Two events, the relationship between two events can be interpreted this way. If A and B are independent, you may interpret that as B is not effective to change A. Like a vaccine is not effective to prevent a disease. Or being like, it doesn't matter if you are a male or female when you are promoted, or paying high tuition or not does not matter when you increase your salary. Or you may interpret this as information about B does not help predict A. So it clearly tells you that you don't need this data. So it's very simple. Or exactly, this is the same interpretation. Between two different groups of about B, the outcome is the same. So there are many ways to interpret the independence depending on the context, and more examples in economics. Today's stock returns independent of tomorrow's. Very interesting. If they are not, there is a momentum. If they are independent, then we cannot predict the future stock returns using the past, right? Or Chinese GDP growth rate independent of the United States GDP growth rate. It's also interesting. Maybe they are not, but if they are independent, then also that implies an interesting economic theory. And independence is very important in many contexts in economics and social sciences and like medical sciences. Also, later you are going to see independence in a theoretical context. When we develop our inference method, we have to assume that observations are independent. So it's one of the most important assumptions, like common assumptions in statistics. In statistics, seriously, everywhere you are going to assume some kind of independence assumption. So that's the definition of independence. And the independence assumption can imply the special multiplication rule. Do you remember the general and special addition rule? It's similar. The structure is the same. Now we had the general multiplication rule in this form. The probability of the intersection between A and B is a multiplication of these guys. But this is not clean. We need to calculate conditional probability. So what you want in the end is that you want to express the probability of the intersection as a multiplication of two simple probabilities like this. To do this, to have this, you need additional assumption, which is statistical independence. Because if they are statistically independent, the conditional probability equals to the unconditional probability. Probability of A is not affected by the condition B. So this is the statistical independence is required assumption to obtain this special multiplication rule. Remember, mutual exclusiveness played the same role for the special addition rule in chapter 1, but there is no relationship between them. So statistical independence has nothing to do with mutual exclusiveness. Don't be confused. So if events A and B are independent, even if they are independent, there is no guarantee that they are mutually exclusive or not. So they may be exclusive or not, and vice versa. If they are exclusive, mutually exclusive, that do not imply they are independent or not. So just they are parallel, the structures are parallel, but there is no direct relationship between them. Okay, I'm going to stop this video here and continue in the next video to see how, in practice, how we can test if two events are statistically independent or not. That's a little bit of algebra. We'll see you in the next video. Thank you for watching the videos.